Hello and welcome everybody. Today we're taking a closer look at the algebraic structure of the complex numbers, and we are going to learn what a field is. The German word is Körper, which also means body. I can't tell you why this algebraic structure is called a body, or in English a field. I don't know the historic reasons for that. But mathematically speaking, a field is a set, and you have two binary operations, addition and multiplication. Binary means you take two elements of this set and you make a new element out of them. In this case, a plus b, which needs to be an element of the set k as well. This is addition, and multiplication, you take two elements and multiply them to get a new element of this set k. And this set, together with these two operations, is called a field if the long list of so-called field axioms hold. I'm a little bit lazy here. I write here, this means for all, meaning for arbitrary a, b, c elements of k, the following stuff holds. Usually you need to write it behind every axiom, but I think this should be enough to put it here. So we want addition to be associative, meaning doesn't matter where we put the parentheses or brackets. I'm not sure which word is the correct one here. Then we need to have a neutral element with respect to the addition, meaning there exists an element of k, usually denoted by 0, such that for arbitrary a in k, a plus 0 equals a. One should also ask for 0 plus a equals a, but since addition is assumed to be commutative, this is enough. The same for the so-called inverse element of addition. For any element of k, I need to be able to find another element such that a plus b equals this neutral element, 0. Usually this b is denoted by minus a. A little bit later we're going to show that b is unique. And as I said before, addition needs to be commutative. These four axioms or laws must hold. The same for multiplication. I need associativity. I need a neutral element. This is usually denoted by 1. And little technicality, 1 is not allowed to be 0, because otherwise if I take k equal to 0, the set containing only one element, then this trivially would be fulfilled, and 0, the set with one element, would be a field. We don't want that to happen, so here 0 must be different from this neutral element 1, and we want that a times 1 equals a, again for arbitrary a in k. And again, 1 times a also needs to be a, but since multiplication must be commutative, it is enough to write this down. And same as for addition, we need the existence of a multiplicative inverse, usually denoted by a to the power of minus 1 or 1 over a, meaning for arbitrary element of k not equal to 0, I must be able to find another element such that a times b is 1, and by commutativity also b times a is 1. And then a very important axiom which connects addition and multiplication is the distributive law, meaning if I have a times b plus c, this must be the same as a times b plus a times c. And here again, this is only left distributivity, but by commutativity of multiplication I can easily show that if this holds, then also it holds if I multiply a from the right. If you're a beginner, you might want to check that. Okay, this is a very long and tedious list to write down. If you are familiar with the notion of a group, then this can be shortened very much. K together with two operations plus and this little dot here is a field if and only if k with respect to plus is an abelian group, and k star, meaning k without the element 0, the neutral element of addition, with respect to multiplication is also an abelian group. These two things together guarantee that you have a field, oh I forgot, and of course I still need the connection between plus and here multiplication, so I must have that the distributive law holds. Well-known examples of fields are, of course, the rational numbers. If you think what you learned in school, you always apply this. Actually use these so much that we do not even care to say now this by associativity we can do this and that, because we learn it from kindergarten on. And also the real numbers. Here, well-known, I bet you never proved that these are fields, that these axioms hold, because that is a whole nother story. And to begin with, you need to define what the rational numbers and, much more difficult, the real numbers are, in fact. And then you have to show that these axioms hold. We're not going to dive into that here, but we're assuming throughout this chapter that we know that the real numbers are a field. And using this, we now prove that the complex numbers, which remember are nothing but two-dimensional real vectors, together with these binary operations of addition and multiplication that we introduced in the first video, that these complex numbers are indeed a field. Now, very important, I used this awkward notation on purpose because when we did arithmetic in the complex numbers using the Cartesian form, we always assumed that these well-known laws hold. So it's a very bad idea to use this notation to prove them, because we already gotten used to it so much that maybe we make a mistake. So for this proof, and after that we're finished with this notation, we're going to use here the plus sign with the circle around and the dot with the circle around, and we use vector notation. Okay, and now by direct verification we go through all the axioms and see if they hold and why this is so. Now, if you're a complete beginner, it's really worthwhile to do each step. If you already know this stuff, you can just say, well, associativity is inherited from R in the sense that because it holds in the real numbers, it follows easily that it must hold in the complex numbers. But we're going to do it. So we have to show that for three arbitrary complex numbers, denoted by these three vectors, this sum is the same as when I move the brackets here. So step by step, we first add these two complex numbers. So we get this, and then we have to add with this complex numbers, and we end up with that. And now this is what the meaning of this is. Here in each entry we are in the real numbers. So here we know, because in R addition is associative, that we can move the brackets. Okay, so we end up with that. And now I make these two steps backwards and I end up with this here. I omitted one step, but I think it should be clear enough. So now we have actually shown that addition in the complex numbers is associative. And as I said, if you have done this once in your life, it's okay to write, well, this is obvious because the addition in R is associative. Second, we have to find a neutral element for this addition. Well, of course, we're going to take the vector 0, 0. And we need to check, although it's almost obvious, but still we're going to do it, that for arbitrary complex number AB, we have that AB plus this neutral element leaves AB alone. So we end up with AB. And here again, because 0 is the neutral element of the real numbers, in each entry a plus 0 is a and b plus 0 is b, so that's exactly what we want to show. Next step, we need to find for an arbitrary complex number ab its inverse with respect to addition. This is also easy. We simply take this vector with minus a and minus b. And then you need to check that ab plus this vector gives 0, which should be obvious. But again, since maybe most of you are beginners, we are going to do it. And indeed, a minus a and b minus b are 0, so we end up with the neutral element as it should be. And finally, for last axiom for the addition, we must show that the addition is commutative. Again, this is inherited from the real numbers, because if I add two complex numbers, I have this. And now, because the real numbers have a commutative addition, I can interchange, and I end up with the commutative law. So now for the multiplication. Associativity is always a drag. Here I think it's okay to say this is inherited from R. If you don't believe me, please, and if you're a beginner, please fill in the dots. You have to prove that this here is this here. Most straightforward method is to just calculate here the left-hand side and see what you get, and then do the same for the right-hand side and compare the two terms, and they will be equal. This is just a lot to write down, but not really difficult. So I encourage you, if you are a beginner, please do this. I'm going to skip this step. So next we need a neutral element of the multiplication. This, as we already know, is the vector 1, 0 lying on the real axis. So let's check that. Checks out. Use the definition of this circled dot, and b times 0 is 0, a times 0 is 0, so you end up with ab as it should be. If you haven't thought about this before, this is kind of hard to find the multiplicative inverse, but we already did this in proposition 9.2, and we already know that this vector here with the entries a over a squared plus b squared, which is nothing but the absolute value of this number squared, and second entry minus b divided by the absolute value squared, actually is a multiplicative inverse. If you don't believe it, please check that this here times this gives you 0, 1. Now for commutativity, we write down the definition. And now, because again in the real numbers we have commutativity of the product, we can interchange here the order. But this here is actually nothing but this product. Yeah, do it from right to left. The definition of dot is exactly that. There. So we have commutativity because this holds for arbitrary complex numbers a, b, and c, d. And now, because of its importance, we're going to verify the distributive law step by step. And again, this should come as no surprise. We're going to use that multiplication and addition in the real numbers satisfy the distributive law. So to start, we add these two vectors, and now we use the definition of complex multiplication. And we end up with this guy, And now we are using that in the real numbers. Multiplication here is distributive. So this is our result. Now the elegant way to finish this proof is to rearrange the terms so that we end up with what we want. Namely, this guy times this guy plus this guy times this guy. If you can't do that, then it's okay to simply write down what I just said and compare the two results, and they will be equal, but we're doing in an elegant way. And here it helps to keep in mind what we want to end up with. We want to have the product of this and this guy, but this we find, oops, I just got stuck. I made a mistake here. This here, of course, is D plus F, so I have BD, and this is what I need, because AC minus BD is the first component of this product. And here, AE minus BF is the first component of this product. So I rearrange, and the same for the second entry, AD plus BC is the second component of this product. And here, of course, I have used that addition in the real numbers is commutative. You should also write that above this equal sign. And now we can split this up using the definition of plus here. And then, as I said, this is exactly what we want to have. This is AB times CD, and this here is AB times EF. And this here is exactly the distributive law that we wanted to prove, and we are done. So from now on, we can, with a clear mathematical conscience, use the fact that in the complex numbers, the same laws of arithmetic hold as in the rational or in the real numbers. We can calculate with complex numbers just as we were used to with real numbers. Of course, it's no fun to do a proof like this for too many times, but I think it's really important that in the beginning you actually fight through all these steps until you have a clear understanding what happens here, what do we use, what do we take for granted, and what do we even have to prove. Okay, this was maybe not the most fun video, but in the next one we're going to have some fun with the field axioms in the complex numbers. Thanks for watching. Stay tuned. Hopefully I'll see you soon.